Picture this: a vast cosmic neighborhood so enormous it defies imagination, where galaxies gather like cities in the night. And yet, some corners of this sprawling expanse hold secrets that leave even the brightest scientists scratching their heads. Welcome to the Local Supercluster, a mind-bending collection of galaxy clusters stretching over 100 million light-years across. Within this cosmic web, strange phenomena lurk: missing dark matter, ghostly voids, and galaxies behaving in ways that shouldn't be possible. Today, we're diving into 25 of the most baffling mysteries hiding right in our celestial backyard. From unexplained radio loops to galaxies that vanish without a trace, each one challenges what we think we know about the universe. So buckle up, because by the end of this journey, you'll see the cosmos in a whole new light, and who knows, you might just uncover a clue that changes everything. Ready to explore? Let's go! Now, let's zoom in on our first cosmic head-scratcher, the Virgo Cluster's missing dark matter. This colossal gathering of galaxies, one of the closest to us, should be packed with dark matter, the invisible glue that holds galaxies together. But here's the twist: when scientists measured its gravitational pull, they found far less dark matter than predicted. It's like expecting a dense fog and instead stepping into a clear sky. Observations from telescopes and gravitational lensing studies all point to the same baffling gap. Some theories suggest the dark matter might have been stripped away by collisions with other clusters, or perhaps our models of how dark matter behaves are incomplete. This isn't just a minor hiccup, it shakes the foundation of how we think galaxies form and evolve. If dark matter isn't where we expect it, what else might we be getting wrong about the universe's hidden scaffolding? One thing's for sure: the Virgo Cluster isn't playing by the rules, and that makes it a mystery worth unraveling. Now, let's journey to a place where the universe seems to hold its breath, the Fornax Void. Picture a vast expanse of space stretching over 65 million light-years, where galaxies should be crowding the scene, but instead there's almost nothing. Just silence. This eerie emptiness, known as the Fornax Void, defies our expectations of how the cosmos should look. Most regions of space are dotted with galaxies, like stars scattered across a night sky. But here, it's as if someone hit the mute button on the universe. So, what could cause such a staggering absence? One idea is that the Fornax Void might be the aftermath of a cosmic tug-of-war, where gravitational forces from surrounding galaxy clusters pulled matter away, leaving behind this barren stretch. Another theory suggests it could be a relic from the early universe, a bubble that never quite filled in during the rapid expansion after the Big Bang. Either way, its existence challenges our understanding of how matter distributes itself across the cosmos. And here's the real puzzle: if voids like this are more common than we thought, what does that mean for the large-scale structure of the universe? Are they accidents, or do they hint at deeper, unseen forces at work? The Fornax Void doesn't just sit quietly. It forces us to rethink the rules, and that's what makes it one of the most intriguing mysteries in our corner of the cosmos. Now, shifting our gaze to another cosmic enigma, let's unravel the twin mysteries of Centaurus A. This galaxy, a chaotic neighbor just over 12 million light-years away, is famous for its monstrous black hole, one that doesn't play by the rules. At its core, Centaurus A unleashes colossal jets of energy, stretching over 1 million light-years into space. These aren't just any jets, they're some of the most powerful in the known universe, blasting particles at nearly the speed of light. But here's where things get weird. When scientists studied the light from these jets, they noticed something bizarre. The way it's polarized doesn't match what our models predict. Polarization, in simple terms, is how light waves align as they travel, and in most black hole jets, it follows a predictable pattern, but Centaurus A's jets, their polarization is scrambled, almost as if something's twisting the light on its way out. This isn't just a small glitch, it's a full-blown rebellion against our understanding of how black hole jets behave. One theory suggests that magnetic fields near the black hole might be tangled in ways we've never seen, warping the jet's structure. Others speculate that hidden interactions within the galaxy's dusty core could be distorting the light. Whatever the cause, these jets are forcing astronomers to rewrite the playbook on how supermassive black holes interact with their surroundings. And that's not all. Centaurus A's defiance might be a clue that other black holes are hiding similar secrets, waiting to upend our cosmic rulebook even further. So, what does this mean for our picture of the universe? If even the most well-studied black holes can surprise us, how many more cosmic curveballs are out there? Centaurus A doesn't just challenge our theories, it dares us to think bigger. And that's what makes it a cornerstone of the local supercluster's greatest mysteries. Now, let's turn our attention to a cosmic relic that's defied the chaos of the universe, the Leo Ring. Picture this, a colossal loop of gas stretching over 650,000 light-years across, drifting quietly in the Leo constellation. What makes this ring so extraordinary isn't just its size. It's the fact that it's survived nearly untouched for billions of years, a pristine time capsule from the early universe. Most gas clouds of this scale don't last long. They're either ripped apart by galactic collisions or collapse under their own gravity, birthing new stars. But the Leo Ring, it's eerily quiet. Despite its immense size, it's barely formed any stars, leaving it as a near-perfect snapshot of primordial gas. Scientists call it a fossil cloud, a rare glimpse into the raw materials that built galaxies. So why hasn't it been disturbed? One leading idea is that it's the leftover debris from a near-miss collision between two galaxies. As they grazed past each other, their gravitational tug-of-war could have stretched a ribbon of gas into this vast ring, leaving it too spread out to collapse into stars. Another theory suggests it might be a failed galaxy, a cloud that simply never gathered enough density to ignite star formation. But here's the real puzzle: the Leo Ring isn't just sitting still. It's moving, and its motion doesn't quite match any nearby galaxies. That means it might not belong to any of them, raising the possibility that it's a wanderer, drifting through intergalactic space like a ghostly remnant of a forgotten era. What's clear is that the Leo Ring challenges our assumptions about how gas behaves in the universe. If something this massive can avoid destruction and star formation for so long, what else might be hiding in the cosmic shadows? It's a reminder that even in the bustling local supercluster, there are still pockets of mystery waiting to be unraveled. And speaking of cosmic mysteries, our next stop takes us to a place where the universe's weather gets downright strange: the Hydra Cluster's cold front. But more on that in a moment. Now, let's dive into something that feels almost like cosmic weather: the Hydra Cluster's cold front. Imagine a massive galaxy cluster, a bustling metropolis of stars and gas, where temperatures should be chaotic and unpredictable. But here's the twist: nestled within this seething hot plasma is a sharp boundary, a dividing line where the temperature suddenly drops like a cold front moving through Earth's atmosphere. This isn't just a minor dip. We're talking about a staggering difference where one side of this front is tens of millions of degrees hotter than the other. What's even stranger, this boundary isn't blurring or fading away as physics would predict. Instead, it's holding its shape with eerie precision, defying the natural tendency of heat to spread and even out. So how does a cosmic cold front stay so sharp? One theory points to magnetic fields. These invisible lines of force might be acting like a shield, wrapping around the cooler gas and preventing it from mixing with the hotter surroundings. Another idea suggests that the front is a relic of a past collision, a shockwave frozen in time, left behind when smaller galaxy groups plowed into the Hydra Cluster. But here's the real head-scratcher: this cold front has survived for hundreds of millions of years. That's like a ripple in a pond staying perfectly still for centuries. Normally, turbulence and cosmic winds would have erased it long ago. Its endurance hints at forces we don't fully understand, perhaps even new physics at play in these extreme environments. The Hydra Cluster's cold front isn't just a curiosity, it's a challenge. It forces us to rethink how energy behaves in the universe's most crowded neighborhoods. And if something this delicate can persist against all odds, what other cosmic surprises are waiting to be discovered? Up next, we'll encounter a galaxy that's more ghost than star Antlia 2, a cosmic oddity with a dark secret. But that's a story for another moment. Now, let's turn our attention to a cosmic enigma that defies expectations, the Antlia 2 ghost galaxy. Picture a galaxy so faint, so wispy, it's barely there at all. Antlia 2 is like a shadow in the night sky, a collection of stars so spread out that it barely registers against the backdrop of space. Yet, despite its ghostly appearance, this galaxy holds a dark secret, one that's rewriting what we thought we knew about dwarf galaxies. What makes Antlia 2 so puzzling? For starters, it's incredibly diffuse. Most dwarf galaxies pack their stars relatively tightly, but Antlia 2 is stretched thin, with stars scattered so far apart that it's almost transparent. If you were to fly through it, you might not even realize you were inside a galaxy at all. But here's where things get really strange. Despite its feeble starlight, Antlia 2 is surrounded by a massive halo of dark matter, far larger than anything its size should have. This mismatch is a cosmic contradiction. Normally, a galaxy's dark matter halo scales with its visible mass, but Antlia 2 halo is enormous, as if it belongs to a galaxy 10 times its size. How does something so faint have such a dominant dark presence? One theory suggests it was once a much larger galaxy, stripped down over time by the Milky Way's gravity, leaving behind only its dark matter skeleton. Another idea proposes that dark matter behaves differently in these tiny galaxies, clumping in ways we don't yet understand. But Antlia 2 isn't just a curiosity, it's a challenge to our models of galaxy formation. If dark matter can outweigh visible stars to this extreme, what does that mean for the hundreds of other dwarf galaxies we've discovered? Could they too be hiding oversized halos? The ghost galaxy forces us to reconsider the rules of cosmic architecture, hinting that the universe's smallest structures might hold the biggest surprises. Up next, we'll unravel another cosmic mystery, the Sculptor Wall, where galaxies align in a way that shouldn't be possible, but that's a story for another moment. Now, let's shift our gaze to a structure in the cosmos that seems to play by its own rules, the Sculptor Wall. Imagine a vast, sprawling sheet of galaxies stretching across millions of light years, a cosmic tapestry woven into the fabric of space. But here's the twist: the galaxies in this wall aren't scattered randomly like confetti. Instead, they're aligned in a way that defies the universe's usual chaos, as if some unseen hand arranged them just so. This peculiar alignment challenges one of astronomy's foundational ideas, the cosmological principle, which states that on large scales, the universe should look roughly the same in every direction, with matter distributed evenly and without preferred orientations. Yet the Sculptor Wall's galaxies seem to huddle together in a coordinated fashion, almost like they're following a hidden blueprint. What could cause such order in a universe built on randomness? One possibility is that colossal tidal forces, generated by the gravitational pull of nearby superclusters, nudge these galaxies into alignment over billions of years. Another theory suggests that the wall might be a fossil relic of the early universe, a structure frozen in time from an era when the cosmos was far more clumpy and uneven. But the implications go deeper. If galaxies can align on such vast scales, it might mean our understanding of cosmic evolution is missing a critical piece. Could there be forces at work we haven't yet accounted for? Or is the Sculptor Wall a rare exception in an otherwise disordered universe? Either way, this cosmic puzzle reminds us that the universe still holds secrets we've only begun to uncover. Up next, we'll explore another anomaly, the Eridanus Supervoid, and its eerie connection to a mysterious cold spot in the cosmic microwave background. But that's a mystery for another moment. Now, let's venture into one of the most baffling corners of our cosmic neighborhood, the Eridanus Supervoid. Picture an enormous, nearly empty region of space, stretching over hundreds of millions of light years, where galaxies are few and far between. But this void isn't just a quiet patch of darkness, it's linked to something even stranger. A mysterious cold spot in the cosmic microwave background, the afterglow of the Big Bang itself. This cold spot is like a cosmic bruise, a patch of the universe that's noticeably colder than its surroundings. At first glance, you might think it's just a random fluctuation, a quirk in the data. But when astronomers noticed that this cold spot aligns almost perfectly with the Eridanus Supervoid, the questions started piling up. Could this be a coincidence, or is there something deeper at play? One theory suggests that the supervoid's emptiness might be the culprit. As light from the cosmic microwave background travels through this vast, sparse region, it loses energy, creating the illusion of a colder spot. It's like walking through a wind tunnel. The journey saps your strength, leaving you a little weaker on the other side. But here's the catch: the supervoid's size and the cold spot's intensity don't quite match up. The void alone shouldn't be able to explain just how cold that spot really is. This mismatch has led to wilder ideas. Some researchers propose that the cold spot could be evidence of a collision with another universe, a fingerprint of the multiverse brushing against our own. Others argue it might hint at flaws in our understanding of gravity or the nature of space itself. Then there's the simpler explanation, that we're just seeing a rare but natural cosmic anomaly, a statistical fluke in an otherwise uniform universe. Whatever the truth, the Eridanus Supervoid and its cold spot force us to confront the limits of our knowledge. Is it a cosmic glitch, a sign of new physics, or just a trick of the light? For now, this eerie pairing remains one of the local supercluster's most tantalizing puzzles. Up next, we'll unravel the mystery of giant radio loops in the Perseus-Pisces filament structures so vast they defy easy explanation. But that's a story for another moment. Now, let's shift our gaze to another cosmic enigma, the Perseus-Pisces filament, a sprawling thread of galaxies stretching across the universe. Nestled within this vast structure are colossal radio loops, mysterious arcs of radio waves so immense they dwarf entire galaxies. These loops aren't just random blips in the cosmic static, they're signatures of something far more profound, yet their origins remain shrouded in mystery. Imagine stumbling upon a set of giant, ghostly rings floating in space, each one spanning millions of light years. That's essentially what astronomers have detected here. These radio loops emit faint but distinct signals, hinting at energetic processes that once rocked this region of the cosmos. But what could have created such enormous structures? One leading theory points to ancient galactic outbursts, cataclysmic events like supermassive black holes spewing jets of plasma into intergalactic space. Over eons, these jets could have expanded and twisted into the loops we see today, like echoes of a long-forgotten cosmic explosion. Yet there's a problem. The energy required to produce loops of this scale is staggering, far beyond what typical black hole activity can explain. Some researchers speculate that these loops might be relics of a titanic collision between galaxy clusters, a violent merger that sent shockwaves rippling through the surrounding gas. Others wonder if they're evidence of an even rarer phenomenon, cosmic strings, hypothetical defects in the fabric of space-time left over from the universe's earliest moments. Then there's the puzzle of their persistence. These loops haven't faded away as quickly as models predict. It's as if they're being fed by some hidden energy source, a cosmic battery we haven't yet identified. Could dark matter be playing a role, or is there an entirely new physics at work here? The Perseus-Pisces filament's radio loops challenge our understanding of how energy moves through the universe. They're a reminder that even in the vast, seemingly orderly cosmos, There are structures so bizarre they defy easy explanation. Next, we'll turn our attention to a supermassive black hole that's oddly quiet, and you see 4889, a sleeping giant with secrets of its own. But that's a mystery for another moment. Now, let's unravel the mystery of NGC 4889, a cosmic giant that defies expectations. At the heart of this galaxy lies a supermassive black hole, one of the largest ever discovered, yet it's eerily silent. You'd expect a beast of this size to be devouring stars and spewing radiation, but instead, it's lurking in the shadows, almost as if it's taking a nap. So why is this black hole so quiet? The answer might lie in its past. Astronomers believe NGC 4889 black hole was once a voracious monster, feasting on surrounding gas and dust in a frenzy of activity. Over time, it may have simply run out of nearby material to consume, leaving it in a dormant state. Think of it like a campfire that's burned through all its fuel. The flames die down, leaving behind glowing embers. But here's where it gets even more intriguing. This quiet phase could be a normal part of a black hole's life cycle. Just like stars, black holes might go through periods of intense activity followed by long stretches of rest. If that's true, then NGC 4889 isn't an anomaly, it's a snapshot of what happens when a supermassive black hole reaches middle age. Yet there's another twist. Some scientists suggest that this black hole isn't entirely asleep. It might still be nibbling on stray gas or even smaller black holes, just at a rate too slow for us to detect. Or perhaps its outbursts are directed in a way we can't see, like a flashlight pointed away from Earth. The silence of NGC 4889 forces us to rethink how black holes evolve. Are they always active, or do they spend most of their lives in quiet retirement? And if they do sleep, what wakes them up? These questions aren't just about one galaxy, they're about understanding the life stories of black holes across the universe. Up next, we'll explore two more cosmic oddities, the M86 galaxy's high-speed gas and UGC 3672 orphan stars, where the universe continues to surprise us. Shifting our gaze to another cosmic puzzle, let's dive into the strange case of the M86 galaxy and its high-speed gas. Picture a galaxy moving so fast through space that it's literally being stripped of its gas, like a car speeding through a downpour, leaving a trail behind. M86 is racing through the Virgo Cluster at millions of miles per hour, and the friction from intergalactic gas is tearing its own gas reservoir away. This isn't just a slow leak, it's a cosmic robbery happening at breakneck speeds. What makes this even wilder is that the lost gas isn't just vanishing. It's forming vast, glowing tails that stretch across space, visible in X-ray images. These tails are like cosmic breadcrumbs, hinting at the violent journey M86 has endured. But here's the kicker. This process could be starving the galaxy of the raw material needed to form new stars. Without gas, M86 might eventually become a celestial ghost town, silent and stagnant. Now, let's turn to an even lonelier spectacle, UGC 3672 and its orphan stars. Imagine a group of stars drifting through the void, untethered from any galaxy, like a boat cut loose from its moorings. These stars weren't born in isolation. They were likely ripped away from their home galaxy during a violent collision or close encounter with another galaxy. But instead of fading into darkness, they've clung together, forming a faint, wandering stream in the cosmos. What's fascinating is that these orphans aren't just random strays. Their motion and arrangement tell a story of galactic violence, a moment when gravity's tug of war tore them free. Studying these stars gives us clues about the chaotic interactions that shape galaxy evolution. It's like finding debris from a car crash, except the crash happened millions of years ago, and the debris is still drifting through space. Together, M86 is high-speed gas, and UGC 3672 orphan stars show us how dynamic and destructive the universe can be. Galaxies aren't static islands, they're constantly evolving, colliding, and shedding pieces of themselves, and sometimes those pieces tell the most compelling stories. Coming up, we'll venture into the eerie emptiness of the Boots Void, where galaxies are few and far between, and the mystery of why they cluster in such unexpected ways. Now, let's journey into one of the most hauntingly empty places in the known universe, the Boots Void. Picture a region of space so vast it could fit thousands of galaxies, yet it's almost eerily deserted. This cosmic desert, spanning hundreds of millions of light years, holds only a handful of galaxies scattered like lone travelers in an endless wasteland. What's baffling isn't just the emptiness, it's how the few galaxies that do exist here cluster together in thin, delicate filaments like beads on a string. According to our current understanding of the universe, matter should be spread more or less evenly, but the Boots Void throws that idea into question. Instead of a smooth distribution, its galaxies cling to these faint threads, as if huddling for warmth in the cold expanse. Scientists have wrestled with this mystery for decades. One theory suggests that the void might be the result of smaller voids merging over time, pushing galaxies into these narrow bridges. Another idea proposes that dark matter, the invisible scaffolding of the cosmos, somehow guided them into these unusual formations. But neither explanation fully accounts for just how empty the Boots Void truly is, or why its galaxies refuse to spread out. What makes this even more intriguing is that these isolated galaxies aren't like the ones we see in crowded clusters. Many of them are oddly quiet, with little star formation, as if the void itself has sapped their energy. It's almost as though the emptiness has a chilling effect on galactic life. Yet, despite the void's desolation, those lonely galaxies tell a story. Their delicate filaments might be remnants of an ancient cosmic web, a ghostly echo of the universe's structure in its infancy. Studying them could help us understand how the largest structures in the cosmos form, and why some regions end up so empty while others teem with galaxies. Up next, we'll uncover another enigma, the Coma Cluster's mysterious dark flow, a movement so strange it hints at forces beyond our observable universe. But now, let's turn our attention to something even more perplexing, a cosmic tug-of-war that defies explanation. In the heart of the Coma Cluster, astronomers have detected a bizarre phenomenon known as dark flow. Imagine hundreds of galaxies all moving together in the same direction, as if pulled by an invisible hand. This isn't just random motion, it's a coordinated drift, and it's got scientists scratching their heads. What makes dark flow so controversial is that it shouldn't exist. According to our understanding of the universe, the expansion of space should be the dominant force, with galaxies drifting apart in a predictable way. But here, entire clusters seem to be streaming toward a single point beyond the edges of our observable universe. It's as if there's a hidden mass out there, something so enormous it's yanking galaxies toward it like a cosmic magnet. Some researchers argue this could be evidence of structures lurking in the unobservable universe, regions so distant their light hasn't had time to reach us. Others suggest it might be a flaw in our measurements, a subtle error magnified by the scale of the cosmos. But the data keeps pointing to something real, something massive, and something we can't yet see. If dark flow is genuine, it could rewrite our understanding of the universe's structure. It hints at the possibility of other superclusters, perhaps even other universes, exerting a gravitational pull on our own. Or it might mean there's a fundamental gap in our theories, a missing piece of physics that could unlock deeper secrets of the cosmos. One thing's for sure, the Coma Cluster's dark flow is a mystery that challenges the very boundaries of what we think we know. And as we peer deeper into the unknown, the next phenomenon on our list takes us even further into the heart of a galaxy that defies expectations. Now, shifting our gaze to another cosmic puzzle, we arrive at Messier 49, a galaxy that's playing by its own rules. Nestled in the Virgo Cluster, this giant elliptical galaxy should, by all accounts, be surrounded by a massive halo of hot gas emitting X-rays. That's what galaxies of its size and type typically do. They trap and heat gas as they grow, creating a glowing X-ray aura. But Messier 49, it's missing that halo entirely, and astronomers are stumped. This isn't just a minor discrepancy, it's a full-blown paradox. The absence of an X-ray halo suggests something unusual is happening with the gas around Messier 49. One theory is that the galaxy's supermassive black hole might have gone through a violent outburst in the past, blasting away the surrounding gas before it could settle into a halo. Another idea is that the galaxy's environment, its place in the bustling Virgo cluster, might have stripped the gas away through relentless gravitational tugs from neighboring galaxies. But here's the twist: Messier 49 isn't alone in this odd behavior. A handful of other massive galaxies also lack X-ray halos, hinting that our models of galactic gas dynamics might be missing a key piece. Maybe there's a phase in a galaxy's life where it stops holding onto its gas, or perhaps the process of halo formation is far more fragile than we thought. Either way, Messier 49 is forcing us to rethink how galaxies interact with their surroundings. What makes this mystery so compelling is that it's not just about one galaxy, it's about understanding the life cycle of gas in the universe. Gas-fueled star formation feeds black holes and shapes the evolution of galaxies. If we can't explain why Messier 49 lost its halo, we might be overlooking a fundamental process that governs how galaxies grow and change over time. As we piece together clues from this cosmic outlier, the next phenomenon on our list takes us even deeper into the unexpected, where gas clouds defy the odds and ancient stars burn brighter than they should. Now, let's turn our attention to a cosmic oddity that defies expectations: the Cain's Venatus I cloud. This vast, drifting gas cloud, nestled within the Local Supercluster, holds a secret that's baffling astronomers. It's packed with metals. And not just a little, far more than a typical gas cloud of its size should contain. Here's why this is so puzzling. In the universe, metals, which astronomers define as any element heavier than hydrogen and helium, are forged in the hearts of stars or during violent stellar explosions. Over time, these metals get scattered into space, enriching surrounding gas clouds. But the Cain's Venatus I cloud's metal content is unusually high, as if it's been drenched in stardust from multiple cataclysmic events. So, what could explain this? One leading theory points to a turbulent past. Perhaps this cloud is the aftermath of a galactic collision or a series of supernovae that flooded it with metals. Another possibility is that it's absorbing material from nearby galaxies, siphoning off metal-rich gas like a cosmic sponge. Yet neither theory fully accounts for the sheer abundance we're seeing. What makes this mystery even more intriguing is that the Cain's Venatus I cloud isn't forming stars at the rate you'd expect for such a metal-rich environment. Normally, metals act as cosmic fertilizers, helping gas cool and collapse into new stars. But here, the cloud seems to be holding onto its riches without putting them to use. It's like finding a treasure chest buried in the desert full of gold but untouched. This enigma isn't just about one cloud. It challenges our understanding of how metals spread through the universe and how they influence the birth of stars. If we can unravel the story behind the Cain's Venatus I cloud, we might uncover new chapters in the life cycle of galaxies. As we ponder this metallic mystery, our journey through the Local Supercluster's unexplained phenomena takes us next to a place where galaxies collide, but not in the way anyone predicted. Now, let's shift our gaze to a cosmic spectacle where the rules of galactic behavior seem to bend, starting with the peculiar case of NGC 1275. At the heart of this galaxy, astronomers have spotted enormous, ghostly bubbles stretching tens of thousands of light years across. These aren't just any bubbles, they're colossal structures of radio waves rising like cosmic balloons from the galaxy's core. What's strange is how they got there. NGC 1275 houses a supermassive black hole, and while black holes are known to spew jets of energy, these bubbles don't match the usual patterns. Instead of narrow, focused jets, the bubbles are vast and diffuse, as if the black hole had a fit of cosmic hiccups. One theory suggests they're remnants of ancient outbursts frozen in time. Another idea, the black hole's activity might be pulsing in a way we've never seen before, leaving behind these eerie, expanding shells. But the mystery doesn't end there. Just as puzzling is HCG 16, a tight-knit group of galaxies locked in a gravitational dance. Normally, when galaxies collide, it's a recipe for chaos. Gas clouds compress, triggering fireworks of new star formation. Yet here, despite the galaxies smashing together, star birth is oddly subdued. It's like watching a car crash in slow motion, but without the expected explosion. Why the silence? Some researchers think the galaxy's gas is being stripped away too quickly, leaving little fuel for stars. Others speculate that turbulence from the collisions is heating the gas, preventing it from cooling and collapsing. Whatever the reason, HCG 16 defies the textbook picture of galactic mergers, forcing us to rethink how these cosmic encounters play out. Together, these two phenomena, NGC 1275 enigmatic bubbles and HCG 16's strangely quiet collision, paint a picture of a universe that's far more unpredictable than we imagine. And as we continue our journey through the local supercluster's greatest mysteries, we'll encounter yet another cosmic head-scratcher, a place where star formation defies time itself. Now, let's journey to one of the most extreme stellar nurseries ever discovered, the Lynx Arc. Nestled in the distant reaches of the universe, this fiery ribbon of light is a window into the cosmos's violent youth. What makes it extraordinary isn't just the sheer number of stars being born here, but the fact that this frenzy of creation is happening in what should be a relic of the past. The Lynx Arc is a snapshot of the early universe, a time when galaxies were smaller, hotter, and far more chaotic. Yet here it is, billions of years later, still churning out stars at a rate that dwarfs anything in our modern cosmic neighborhood. Imagine a fireworks display that never ends, each explosion triggering another, in a chain reaction of stellar birth. That's the Lynx Arc, but how can such intense activity persist for so long? Normally, regions like this would exhaust their gas or be disrupted by galactic collisions. One clue lies in its isolation. The Lynx Arc sits in a pocket of space relatively untouched by outside forces, allowing its star-forming factories to keep running unchecked. Another possibility is that it's fueled by primordial gas, material so pristine it hasn't been polluted by heavier elements, making it easier to collapse into new stars. Yet even these explanations leave gaps. Why hasn't the gas cooled or dispersed? Why does the Lynx Arc defy the quiet fate of most ancient structures? Some theorists suggest it's caught in a rare cosmic equilibrium, where gravity and turbulence balance perfectly to sustain the chaos. Others wonder if we're seeing the aftermath of a colossal collision, a shockwave frozen in time. Whatever the answer, the Lynx Arc challenges our understanding of how stars form and how long the fires of creation can burn. And as we unravel its secrets, we're reminded that the universe still holds pockets of its wild, untamed past. Next up, a structure so vast it might rewrite the rules of cosmology itself. Now, let's turn our attention to something so enormous it seems to defy the very rules of the cosmos, the Hercules-Corona Borealis Great Wall. This mind-bending structure stretches across an astonishing 10 billion light-years, making it one of the largest known formations in the universe. But here's the catch: its sheer size might actually break the limits of what we thought was cosmologically possible. According to our current understanding, the universe should be relatively uniform on the largest scales, a principle known as the cosmological principle. Inflation theory, which explains the rapid expansion of the early universe, predicts that no single structure should exceed around 1.2 billion light-years in size. Yet the Hercules-Corona Borealis Great Wall dwarfs that limit nearly 10 times over. So, is this a flaw in our models, or is there something extraordinary at play? Some scientists argue that this wall isn't a single coherent structure, but rather a chance alignment of galaxy clusters, a cosmic illusion created by our limited perspective. Others suggest that it might be evidence of exotic physics, perhaps relics from the universe's infancy that survived inflation in ways we don't yet understand. There's even speculation that it could hint at a deeper layer of cosmic structure, one that operates on scales we're only beginning to grasp. What makes this debate so fascinating is that it forces us to question the very foundations of cosmology. If structures like this truly exist beyond theoretical limits, does that mean inflation theory needs revising? Or are we simply seeing the universe in a way we haven't before? Either way, the Hercules-Corona Borealis Great Wall stands as a humbling reminder that the cosmos still has surprises up its sleeve, and that some mysteries are too big to ignore. Next, we'll explore a tiny galaxy with an enormous secret. Now, let's zoom in from the vastness of the Hercules-Corona Borealis Great Wall to something much smaller but no less puzzling: the Segue 1 dwarf galaxy. At first glance, this tiny galaxy might seem insignificant, but don't let its size fool you. Segue 1 holds a cosmic secret that's turning our understanding of dark matter upside down. Here's the mind-bending part: 99% of Segue 1 mass isn't even visible. That's right, this galaxy is almost entirely made up of dark matter, the mysterious substance that doesn't emit light or energy but exerts gravitational pull. For comparison, most galaxies, including our Milky Way, have a dark matter makeup closer to 85%. So why is Segue 1 practically drowning in the stuff? Scientists are stumped. One theory suggests that Segue 1 might be a failed galaxy, a cosmic relic that never managed to gather enough regular matter to form stars efficiently. Another idea is that it's a surviving fragment of an even older galaxy, torn apart by gravitational forces, leaving behind this dark matter-rich remnant. Either way, its existence challenges the lower limits of what we consider a galaxy. How small or dim can a collection of stars be and still earn that title? What makes Segue 1 especially intriguing is that it could be a window into the universe's earliest days. Its extreme dark matter content might mirror conditions in the primordial cosmos, offering clues about how the first galaxies assembled. Or perhaps it's hinting at something even stranger: that dark matter behaves differently on tiny scales than we've predicted. As we piece together the puzzle of Segue 1, one thing is clear: this unassuming dwarf galaxy is forcing us to rethink the rules of cosmic construction. Next up, we'll tackle a collision closer to home that's not happening quite the way we expected. Now, let's turn our attention to a cosmic event that hits a little closer to home: the inevitable collision between our Milky Way and the Andromeda Galaxy. You'd think something this monumental would have a straightforward timeline, but the universe loves throwing curveballs. Here's the thing: scientists agree that these two galaxies are on a collision course, but when it comes to the when and how, the predictions are all over the place. Some models suggest the encounter will happen in around 4 billion years, while others push it closer to 5 billion. Why the discrepancy? It all comes down to how we measure Andromeda's movement. Andromeda is hurtling toward us at roughly 110 kilometers per second, but its path isn't perfectly straightforward. Tiny uncertainties in its speed or trajectory, things like gravitational nudges from other galaxies or the distribution of dark matter, can add up to massive differences over billions of years. Think of it like trying to predict where two cars will collide when one's speedometer might be off by just a few kilometers per hour. Over a long enough distance, that small error changes everything. Then there's the how. Will it be a direct hit or more of a glancing blow? Earlier simulations suggested a head-on crash, but newer data hints at a sideswipe, a slower, messier merger that could stretch across billions of years. Instead of a single apocalyptic collision, we might see a series of near misses and gravitational tugs, gradually pulling the galaxies together. What's really wild is that by the time this plays out, Earth, if it still exists, won't be in much danger. The spaces between stars are so vast that actual stellar collisions are unlikely. But the night sky, that'll be a showstopper. Imagine Andromeda growing from a faint smudge to a sprawling, star-filled disk, eventually merging with the Milky Way into one giant elliptical galaxy. So why can't we pin this down? It's a reminder that even with cutting-edge tech, cosmology is full of educated guesses. The farther we look into the future, the fuzzier the math gets. Next up, we'll explore a mystery that's not about what's coming, but what's pushing us away. But while we're looking ahead to galactic collisions, let's shift our gaze to something far stranger happening right now, an invisible force nudging our entire galactic neighborhood. The Local Void, a vast, nearly empty region of space bordering the local group of galaxies, isn't just sitting there quietly. It appears to be pushing us away. At first glance, this sounds impossible. How can nothingness exert force? Yet multiple studies show the local group home to the Milky Way and Andromeda moving at over 600 kilometers per second relative to the cosmic microwave background. A chunk of that motion seems directed away from the Local Void. It's as if this cosmic desert is repelling us. Scientists have two competing explanations. One suggests the void's emptiness creates a kind of gravitational deficit. With fewer galaxies pulling inward, the denser surrounding regions, like the Virgo Cluster, tug harder, effectively shoving us away from the void. Think of it like sitting on a deflating air mattress. The firmer ground nearby forces you to slide off the sagging middle. The other possibility, we're misreading the data. Measuring large-scale flows in the universe is notoriously tricky. Dust, unseen dark matter, or even errors in mapping galaxy distances could skew results. Some argue the push might just be an illusion caused by incomplete observations. What makes this mystery so compelling is its stakes. If the void's repulsion is real, it hints at gaps in our understanding of gravity or the distribution of dark matter. If it's an error, it exposes blind spots in how we chart the cosmos. Either way, this quiet expanse of nothing might hold answers to some of astrophysics' biggest questions. And with that, we've reached the end of our journey through 25 of the local supercluster's greatest enigmas, from missing dark matter to ghostly galaxies. But remember, space never runs out of surprises. Which of these phenomena left you the most awestruck? Let me know in the comments, and don't forget to subscribe for more deep dives into the universe's endless mysteries. The cosmos is always whispering new secrets, we just have to listen. Now, circling back to where our journey began, let's take a closer look at the Virgo Cluster's missing dark matter, a puzzle that's only grown more intriguing with time. When we first touched on this, we talked about how galaxies in Virgo seem to move as if there's far less dark matter tugging on them than our models predict. But what's happened since then? Fresh observations and bold new ideas are shaking up the conversation. Recent surveys using ultra-sensitive instruments have confirmed the anomaly. Some galaxies in Virgo are orbiting so fast that, without enough dark matter to hold them together, they should have flown apart long ago, yet here they are, defying expectations. One leading theory suggests dark matter might interact with itself or ordinary matter in ways we haven't accounted for, perhaps through unseen forces or particles. Others propose something even more radical, that our understanding of gravity itself is incomplete. Enter modified gravity theories like MUND, which tweak Newton's laws to explain galactic motions without invoking dark matter. While these ideas remain controversial, they've gained traction as tools like the James Webb Space Telescope peer deeper into Virgo's quirks. Meanwhile, projects like the Dark Energy Survey are mapping the cluster in unprecedented detail, hunting for hidden pockets of dark matter or subtle gravitational oddities. What's at stake here isn't just one cluster's mystery. If Virgo's missing dark matter points to new physics, it could rewrite the rules for how all galaxies form and evolve. Or if it's a fluke of measurement, it'd force us to rethink how we study cosmic structures. Either way, Virgo's enigma reminds us that even our best theories are works in progress, and that's what makes astronomy so thrilling. As we wrap up this deep dive, keep your eyes on the cosmos. The next breakthrough might be just a telescope's gaze away. Now, let's shift our gaze to one of the most mind-bending mysteries in our cosmic backyard, the Eridanus Supervoid. Earlier, we touched on how this vast, empty region in space is linked to a puzzling cold spot in the cosmic microwave background. But what if this void isn't just an oddity? What if it's a window into something far stranger like other universes? Some theorists propose that the Eridanus Supervoid might be a cosmic bruise, a dent in space-time left by a collision with another universe in the multiverse. Imagine bubbles floating in foam, each bubble a separate universe. If two bubbles brushed against each other, the energy released could leave behind a void like Eridanus. It's a wild idea, but it's not pure fantasy. Quantum foam theories suggest that at the smallest scales, space-time is frothy and unstable, potentially allowing for such interactions. Others argue the void could be evidence of a universe fingerprint, a remnant from before the Big Bang, when our universe might have been shaped by forces beyond our current physics. While these theories are speculative, they're fueled by the void's sheer size and its eerie alignment with the cold spot. If true, it would mean our universe isn't just one isolated story, but part of a sprawling, infinite multiverse. Of course, skeptics point out simpler explanations, like measurement errors or gaps in our understanding of cosmic inflation. Yet the allure of the multiverse keeps the debate alive. Projects like the Euclid Space Telescope are now scanning the void for subtle clues, tiny distortions in light or unexpected patterns that could hint at unseen dimensions. Whether a gateway to other realities or just a cosmic coincidence, the Eridanus Supervoid challenges us to think bigger. After all, the universe has a habit of being stranger than we can imagine. And who knows, the next great discovery might not just rewrite our textbooks, it could reveal we're not alone in the grand scheme of things. From the eerie silence of the Fornax Void to the cosmic push of the Local Void, these 25 unexplained phenomena in our local supercluster aren't just curiosities, they're cracks in the foundation of modern astrophysics. Each one forces us to question what we think we know about dark matter, galaxy formation, and even the very fabric of space-time. The Virgo Cluster's missing dark matter defies gravity's rules. The Hercules-Corona Borealis Great Wall stretches so vast it might break cosmic limits, and the Eridanus Supervoid, it could be a scar from a multiverse collision or a relic from before time began. These mysteries remind us that the universe is far weirder than our textbooks suggest. Every odd alignment, every unexplained void, every silent black hole is a clue waiting to be deciphered, a puzzle that could rewrite science itself. So tell us, which of these cosmic enigmas captivates you the most? Is it the ghostly Antlia 2 galaxy barely holding itself together, or the Lynx arc blazing with ancient starlight like a fossil from the dawn of time? Drop your thoughts in the comments below. We'd love to hear which mystery sparks your curiosity. And if you're hungry for more deep dives into the universe's greatest secrets, don't forget to hit that subscribe button and ring the notification bell. The cosmos is full of surprises, and we're just getting started. Until next time, keep looking up, because out there in the vast dark, the next great discovery might be